My name is John Delaney. The focus of this lecture is the question, what paths technology, science, oceans, and humans? And of course, no one can answer that. What I'd like to do is at least let's open the dialogue and begin talking about it. And it really is a dialogue. Perhaps all of us will be involved. The current observing systems that we have now in oceanography are more or less captured here. The ship mapping, a satellite flying and mapping the sea surface temperature, which is in red, yellow, and sort of dark blue, and the various platforms, the mobile platforms, 4 of them down below at the bottom, and then a mooring, which stays out for about a year and is anchored to the sea floor. Those are the capabilities that we have that are fairly routine now, and they have evolved from working with many different kinds of technologies. So, next generation ocean science and education, what are we doing now? How are we preparing for the next generation? Well, I'd like to talk with you about this because this is about complexity. I showed this image last time. I show it again because it shows how complicated the ocean actually is. And I've only got about 10 to 15% of the processes that operate within the oceans. And they don't just operate independently. They all operate interactively. So if you change anything, you change the salinity, then you change the density, and you change the currents, and you change the life forms that live in that environment, and you change the oxygen content because it begins to flow in a different way. So all of these are related to one another. The incoming sunlight, the winds, the tides, everything is related in the oceans. And yet we don't understand the ocean very well. And yet we're dependent on it. And this is only the upper part. This is the part driven by the solar energy. The part driven by internal energy is actually as dynamic in a different way. I mean, you tend to think of plate tectonics as, you know, it's pretty slow, you can yawn. But the fact is you don't yawn during a magnitude 9 earthquake. And that is the result of plate tectonics. You don't even yawn during a 7.5. So the ocean has absorbed the input from both of these energy sources, and it is very complicated. Life and the planet and the ocean co-evolved for at least 4 billion years. So there's a new phenomenon on the horizon called ocean observatories, concerted efforts to look at, in detail, at portions of the ocean with the idea that eventually we want to study the entire ocean, but we want to study some places, carefully chosen places, very, very thoroughly. And the National Science Foundation started the Ocean Observatories Initiative, and the reason was that the oceans are very complex and they are central to the quality of life. They are changing very rapidly, but not very predictably. And the sophisticated models we need to make them predictive require new kinds of data. The oceans are fairly dangerous, they're difficult to study, they're very expensive. They have major human impacts on, as we've talked about, resources and hazards. And many of us believe that the Ocean Observatory Initiative and others like it in other countries can transform the interaction between human beings and the oceans. We hope people will become more aware. So these are the, I won't belabor you with this, but these are the major themes underlying NSF's investment of about $700 million. So it's a NASA-scale investment by the National Science Foundation in a program to study the ocean in a more comprehensive and a more sustained manner for decades. But be aware that those are the central themes. Every single one of those themes can be approached by one or another aspect of this Ocean Observatories Initiative that I'm about to share with you. On the left-hand side, you see a small picture, and I will show you a bigger picture here. Their initiative was started formally in 2009. We started talking about this in 1991. So it has taken a very, very long time to get this entire program off the ground. All the output of all the sensors in the entire system, almost 800 different kinds of sensors, or different sensors, and up to 50 different kinds of sensors, will send information back to shore, and a cyber infrastructure will make it available to all people everywhere via the internet. If you can log on to the internet, you can get the data that's coming off of this system. And this is what it looks like. You see those two round circles? Those are two sites, one in the Argentine Basin and one in the Southern Ocean at 55 South. Those are installations. They will be in another 6 months. And then there are four installations in the Northern Hemisphere, one off of Greenland, one off of what's called Station Papa off of the straight west of the Queen Charlotte's, and then one off of Arcos and one off of New Jersey. I will talk to you about the regional scale nodes and the endurance array. One of our foci is long-term change, and the other is something we've never been able to do very well, and that is significant events. We want to be able to do science in the middle of a hurricane or in the middle of an erupting underwater volcano. That's a challenge. That's a challenge. And tsunamis, we want to be in the midst of the generation of a tsunami. What actually happens in detail at the site that these things take place? You remember the eastern boundary currents? I'm showing them here. Well, the one off of our coast, it looks something like this, and I want to talk to you about the climate change, and that is that major weather systems of North America basically come from this region. A lot of the energy comes off the ocean and is acted upon by the jet stream, and there are polar incursions from time to time, but the weather moves from west to east across our country from this area. Pacific decadal oscillations and El Nino constantly change the conditions that we receive on land and that impact the oceans. But this is an excellent place to study such things. Ocean acidification is more accentuated in this area than it is in many others, and folks at NOAA here in town, Dick Feely and others, have launched a major program to study ocean acidification. We hope to be able to contribute to that. The oxygen depletion that I showed pictures of gaping fish mouths and harmful algal blooms, HABs, actually take place offshore. We need to be in the environment in order to understand how these things happen. And then I suppose the moonshot of oceanography is to understand the relationship between turbulence and marine ecological systems or ecosystem dynamics. It's a very complex discussion, and I hope we'll touch on it later. Let's shift to the seafloor. What you're looking at in red are the youngest rocks on the planet. You can say that anything that's in that red zone is less than 1 million or 2 years old, and the ones that are right on the top of it may be weeks to months to years old. On the dark blue in the Western Pacific, that color represents 200 million years old. So the sea floor is nowhere older than 200 million years. And the continents in many places are at least 3 billion to 3.9 billion years old. So the message is that plate tectonics redoes the sea floor on a regular basis by moving around plates. And here's a picture of the plates. Notice I'm fading it directly in. I'll go back and show you that again. Notice that the youngest rocks on the planet are located along the boundaries of the tectonic plates. One-to-one correlation. So as the plates move apart, for one reason or another, molten rock wells up in there and forms new seafloor, causing the magnetic anomalies that we just heard about earlier. So hopefully these threads are beginning to weave themselves together in a tapestry within your mind. Here is the part of the Juan de Fuca tectonic plate that is just off our coast. The smooth blue in the center middle part of the lower and center part of the area is the Juan de Fuca tectonic plate. The subduction zone is where the plate plunges beneath North America, creating the Cascade volcanic range. And the spreading center is where the seafloor pulls apart. The magnetic anomalies line up on that. That's the picture I showed you earlier with the colored magnetic anomalies. That's how folks from here, Dean McManus and others, were involved in that process. Dean is here in the audience. He's a faculty member from the university here. Here's what it looks like if I roll it up to the north and we take a gigantic knife and cut through the ocean floor. This is what you're looking at as a cross-section. The bulb of bright orange is magmatic material that collects as a result of the upwelling of the mantle. It solidifies into the lithosphere, which is the Juan de Fuca tectonic plate, which moves at about 3 to 4 centimeters a year to the east, and at about 10 million years old, it plunges beneath North America and begins to melt over there on the right-hand side. That's what's going on beneath your feet right now, that process. And one of the events, right on top of that bulb of hot rock creating the plates, is axial seamount, which you will hear more about. And there is a sketch of axial seamount with the magma beneath it. And there are two plumes, a black one coming out that's right near its constant plume, and then the event plume, which is the result of a magmatic eruption. Those are two different kinds of beasts. We'll talk more about those as we go. Now, let's introduce the concept of power and bandwidth, the electrical power and the bandwidth. The orange cable that you see there in the middle of the Juan de Fuca tectonic plate has these characteristics. There are two cables, 10 kV power on them, and are up to 8 kilowatts, up to 240 gigabit per second bandwidth on those cables. There are 7 primary nodes offshore that are like big substations, if you have ever seen where the high tension lines come into a substation. We have that, effectively that on the seafloor. I'll show you one of those. And it's also a switching station for bandwidth. And then it's a highly expandable system because we're only using about 15% of it. And we have part per second timing. So we will have this capability offshore for the first time in the ocean. Why would you care? Well, one reason you'd care is you're paying for it through the National Science Foundation. Another reason you care is we will be able to turn your internet into the equivalent of the night sky. People are fascinated by astronomy because they have a chance to look at the night sky, and there's a whole culture about exploring outer space. Well, we don't explore inner space very much, nearly as much, but by putting fiber into the ocean, we can have all sorts of capability that come back instantaneously and are made on the internet, and you can actually begin using something like this to actually look at any part of the ocean within 5 years. We are not alone out there. The Canadians have that loop to the north, and it's called Neptune, and the one in the south was once called Neptune US compared to Neptune Canada. And you can, by the way, see the light blue arrow. That is the California current, right on top of the California current. So here's the underwater volcano, axial volcano that I talked about. We'll talk a little bit more about it, but I just wanted to show you where it is. It's out on the western side of the plate, and you can see over there in the upper left. I won't dwell on this too much. Then there is the axial volcano on that axial volcano. This is the caldera. This is the floor. We'll come back and look at the floor in a minute. But I showed you where the eruption took place. And these are where the cable comes across that floor of the volcano where you saw the lava earlier. And so we have carefully configured it so that the instruments that we're putting out on here will not be interrupted by the next lava flow. We're pretty sure. There's risk everywhere. The next issue is the base of axial, which is down the slope of the axial, is about 2,900 meters. And we have all sorts of instruments, plus a high-rise mooring, which I'll show you much more closely. But you can see sort of a triangular shape with a yellow box at the top there in the middle of the diagram on the left. We'll come back and look at that. This is pretty exciting. This is a next-generation capability. And one of the key engineers is here in the audience. The next one, this shows in more detail the bright yellow box in the upper left. And then the module that looks like a pea pod is only about 6 meters long, and it has the crawling ability to go up and down a cable that's 3,000 meters long. So it can crawl up and crawl back down, making measurements as it goes. I talked to you about methane hydrates. There is a feature out on the continental shelf that is known as Hydrate Ridge, and this is Hydrate Ridge right here, and the fiber, the white lines, are coming in there. We're going to instrument the entire thing. We'll be able to look at all the changes that take place and the massive bubbles that come off on a regular basis from the sea floor. We will be studying a hydrate system like nobody has ever studied it before anywhere. This is the switching station. This is the substation. This is on the seafloor. The big fiber, the cable goes into this thing and comes out the other side. And it is a substation, basically. And all the power is available from there to go out in octopus-like directions with smaller cable that is usually orange or bright yellow. Comes out of this to the instruments that are nearby. And this is one of those secondary nodes. It stands off from the big node, the primary node, and it has the ability to step the power and the bandwidth down to usable levels for the instruments that are involved. We have about 25 of those that will be on the seafloor by this end of summer. This is a close-up of the mooring. You'll see the beam pod. That's called the deep profiler. Here's the 200-meter platform, which is on two-legged mooring. And coming up and down from that one will be this shallow profiler with many instruments on it. All of these will have instruments, and we'll be able to control everything they do offshore from on land. And Eric, can you put your hand up in case people have a special question? Eric was critically involved. And Skip, these folks, if you need to talk about any of this, these are the engineers that are directly involved in producing exactly this system. Now here's what it looks like when it works. The shallow profiler is under total control from land, and it has many, many instruments that can measure all sorts of things, including it can pick out layers, thin layers of these copepods, which are one of the main producers off the coast of Washington, Oregon. So we'll be able to see that, and you'll be able to see it in real time on your computers because we'll be looking at things that nobody's been able to see before. We've only recently discovered the thin layers, but there's massive productivity in those layers between two water masses. And then this other one goes from the deep seafloor up to 200 meters. So we're covering the entire water column with that one plus that one. It's really exciting. It's very, very exciting. And this is overwhelming for you. And it's not intended to be, but on the right is a list of all the instruments. And this is, for me, from my point, is a very elegant instrument. This is a camera. It's a high-definition camera which can pan and tilt and zoom. And it is focused on a hydrothermal vent called Mushroom. And it is very, very exciting that we will be able, from land, to be able to scan around. We can scan around 180 degrees. We can actually home in and look as if we're only about 10 centimeters away from the zoom, and we can move up and down. We can look at anything within that 180 degree. Now, in 5 years' time, I hope to have the thing on wheels, but right now, this is what we've got. I mean, if they can put wheels on Mars, God, you know, we ought to be able to, at least water wings. So here's a better look at axial. That's the caldera. You see the depression in the middle. The orange is shallower. The yellow is deeper. And you see where the little illuminated circle is. It's way offshore. It's on the spreading center of the Juan de Fuca Ridge. It's where the seafloor is pulling it apart. Both sides are coming apart at about 6 centimeters a year. And so let's look at that a little bit. These are the cables and the instruments, and I don't know if you can read them, but I just want to show you. It's about 3 kilometers across the caldera and about 7 kilometers long. You know, so that's a big part of Seattle. And you know, if you could walk down there, it would take you a while to walk across it. And it's rough lava, but we fly in a robot that's on the end of a tether from the ship. I'll show you that in a bit. Here's the hydrate deposit over, and you see where the illuminated circle is over there. It's right near the Continental Shelf. And watch, we'll go in closer, and that's, I showed you that a minute ago, but look what it's looking at. Those are patches of microbial concentrations, and although you can't see it here, periodically there are massive amounts of bubbles of methane that come bubbling out, and then it stops. And then it starts up again, and then it stops. We don't understand that. Nobody understands that. But we'll have cameras there, we'll have mass spectrometers there, we'll have all sorts of things, and we'll have earthquake sensing devices, we'll have seismometers. We'll be able to tell what's controlling this system, which nobody has ever been able to understand. And there's 10,000 gigatons of methane hydrate around the Pacific Rim. And it may be of value to us, but it's distributed through the rocks. It's not easy to pump. It's not easy to mine, but we need to understand it. The Japanese are putting huge amounts of energy into trying to figure out how to use it. But methane is 25 times more significant as a greenhouse gas than CO2. So if there are gigantic belches of methane coming out of these systems on a regular basis, it's something we need to know more about, so that we need to be aware. A magnitude 9 earthquake under exactly this site might release massive amounts of methane. Maybe that's one of the things that tilts us into or out of ice ages, something of that sort. There's so much about the ocean and about the planet that we don't understand. And we are on the threshold of being able to do it. Here's a video showing what that material looks like. That's all microbes there with methane just beneath the surface. And we're taking a sample that's about 3 inches across. And students and faculty have been studying this core, which is taken, and they will be looking at everything that lives in there and everything that it does to everything else. And they'll even be doing genomic analyses. This is the Continental Shelf. So the dark blue is the bottom of the Continental Shelf. That's 2,900 meters. And up in the bright, the dark red on the far right, it's almost to the shoreline. And these are all the instruments that are going to go in that area. The hydrate ridge is in the middle of that. And these profiling moorings are on the left. Now, here is where the data will go. And I don't know if you folks can see this, but I just want to sort of let you know that out of Portland and Seattle will come information that is going to be going to Thailand, Taiwan, Japan, Qatar, Singapore, Japan, New Zealand, Japan, Mexico, South America on these cables. And all the way across the other side over there as well. So we will have a global network capability of taking unbelievably difficult to obtain imagery and analyses and observations and data of all sorts relayed to people across the world. For me, it's just very exciting. So the construction is in effect right now. This is the ship we use. It's the Thomas G. Thompson. We're going out, as I mentioned, see in the lower right there on the bottom. Last year it was 47 days at sea. This year it's going to be 83 days if you want to go offshore with us and you don't get seasick. Maybe you'd like to go. That yellow box there on the fantail is the ROPOS, the ROV that we use. Here is the ROV. It's a robot on the end of a string, and pitched underneath it is a reel of secondary cable, which comes from the primary box, the big switching station, out maybe 2 to 4 kilometers to instruments that are scattered around the floor of the caldera or scattered around in the hydrate ridge area. And here's what we went to sea with, and we laid all that cable on the seafloor last year. We're going to lay just as much this year, and then we'll put instruments, and robots out all this year. All connected, all live by the end of this year. Hopefully on November 20th when I come back, I'll be able to show you data directly coming from the seafloor on that screen. This is the primary node, and the robot grabs these plugs. This is a dummy plug, grabs that, pulls it out, and then takes another plug that's on the cable and plugs it in here. So that's the mechanics, and you can see there are 2 plugs here, and on the other side there are others. This is a complicated thing to do, 1,500 meters underwater from a ship with a robot. It's not so easy to do. It's fun though. It's exciting. It's the kind of thing that you would like your kids to begin to sort of see, God, I wonder if I can get involved in that. Wouldn't that be cool? I could live my life doing that. Again, I emphasize this stuff on the seafloor. I won't beat that to death. The camera again, I love this camera. I love it, I love it. And here's what the camera can see. There's something like mushroom, and that's what the camera can see. And we can control that. In fact, if you have the right pedigree, I suppose, meaning either money or position or influence or whatever, we can transfer control of this to your laboratory or to your group or something, and you can be sort of oceanographer for a day and run this thing and do an educational program of some sort. There's lots of potential here. And here, the key to understanding what goes on in a submarine hydrothermal system is what happens when the earthquakes come. The rhythms of a submarine hydrothermal system are not tied to the weather, we don't think. They may or may not be tied to the tides, but they are certainly tied to the onset of earthquakes. And this is a seismometer, a short period seismometer, which you're putting in place. It's on a tripod so we can level it up. We orient it toward the north so we know exactly where it is and it's perfectly level. It takes a while to do this, but we will have many of these on the seafloor by the end of the year. These are the people that are involved in the program, and I didn't want to put this at the end because, you know, everybody's looking to get out the door. I just wanted to, these are really exciting people. Imagine working with people that you not only respect them and they're very productive, but you like them. That's what this is about. These are sort of the folks that oversee the program. That's Deb Kelly there. I just introduced her. Mike Mulvihill next to Deb is the project manager. Mark Stormer, we should give a moment of applause. He does all the graphics. Right now, Mark Stormer. And Nancy Penrose has a golden tongue that flows through her pen. I don't know if that's a bad metaphor. Anyway, that's Nancy. And then the rest of these folks are part and parcel of the program. I won't go through all the names. The engineers, this is like the, you know, if you have a tank, I hate to use military metaphors. If you had a tank, then the treads on the tank would be the engineers. The whole program runs on the engineers. Gary Harkins in the upper left, Mike Harrington next to him, and Chuck McGuire next to him, and many of the others. This is Eric here. Eric, put your hand up. And Skip. So this is what this group is like, and it's unbelievably good group to deal with. We work really well together. And here are the students, a small smattering of all the students we have taken to sea with us. We take, on average, what, Debbie, 20 to 30 a year on the Thompson, the Thomas G. Thompson, which is state ship, and they are part and parcel of everything. We do not, it's not a classroom. They're immersed in the whole process. They take responsibility. Future science, where are we going? Where might our children go? Well, think about this. This isn't a ship we're talking about. And I get criticized for that. Well, you know, once you put the cable down, you can't move it. Well, no, ships move, but they can only be in one place at one time. This thing could be the size of the tectonic plate, and it could be everywhere all the time, with all the data flowing back all the time to all the people. That's different than a ship. It's complementary to ships. It's important to think of it that way. And this is only 10 examples of the kind of research that can be done simultaneously in the same area. This is a very different way of doing science. When a ship is out for physical oceanographers doing a particular study of currents, that's what they do. Or if it goes out with geologists to study the seafloor, that's what they do. We can do it all the time, made available to all the people for both science and education. So here's, in a nutshell, it's a mesoscale to microscale. Meso means medium scale in the ocean. That's 100 kilometers or more, or up to maybe 200-300 kilometers. That's mesoscale to microscale, which is anything you want down to genomes, yeah, or certainly at least to microbes and viruses. So these are arrays of multidisciplinary sensors that they respond to energetic and transient events while collecting long-term data. They detect, diagnose, and correct malfunctions. So we can do like they do with satellites and platforms in outer space going to other planets. We can log into them and we can fix things because we have, literally, we have control from land over what's going on. We can actually even put new programs out there and back. We can do all sorts of things. So it can also help develop new kinds of technologies, and it is an ideal citizen science educational outreach tool. Ideal. Now, where do you live? You live here. You know where Seattle is. You can see Puget Sound up there. This is what's going on offshore. This is what affects you. 50 millimeters a year, 43 millimeters a year, 36 millimeters a year. That plate's coming toward you, toward us right now. Slowly, 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 and it sticks. And it sticks, and it sticks, but it keeps moving. And it builds up a lot of tension, and the surface of the continent rises a bit until it comes unstuck, and that's a magnitude 9 earthquake. That's what's going on here. That's where you live. This is the Pacific Rim that you live on, and you see that red zone in the subduction zone, that lock zone, that's the part that sticks. Why, we don't quite know. Sometimes it comes unstuck, but boom. When it comes unstuck, that's bad news. Well, it turns out that in the audience there's another gentleman, Jerry Peros, sitting just here, who has built an unbelievably sensitive pressure sensor, which can tell us when the seafloor and the edge of the continent is actually rising. It's down to way, way less than a millimeter, thousandths of an inch. And that's going to be recorded in real time. So unlike almost everybody else around the Pacific Rim, with the possible exception of the Japanese, we will have the data flowing back to us telling us, what's the seafloor doing? What are the tiny earthquakes doing? How is it changing? How much of this is the plate coming ashore? These are exciting moments for us. And here is an example of an array that might be on the continental shelf slope environment. All of these things, I won't read them to you, but each one of them is really fascinating. They're all connected to that secondary node, which is connected to the primary node on the cable. And this is the view of the entire Pacific Northwest, all the way from Cape Mendocino down to the lower right, all the way up to the north end of Vancouver Island. We need to instrument this entire thing, which is capable of killing hundreds of thousands, and is certainly capable of causing many, many tens of billions of dollars worth of damage. This is something in the future, with fiber and other approaches offshore, we can do things like this. What other things for the future? Well, physical oceanographers have been measuring currents and temperatures and salinity for a long time. They're very good at it. Chemical oceanographers have gotten to the point where they can actually measure salinity, and they can measure trace elements of this and that, and they can do all sorts of things chemically. The biologists have had cameras, yeah, but in the last 2 decades, there's a brand new thing emerging, and it's genomics. The capability of doing genomic analyses offshore without being there is just around the corner. And this was put together by Ginger Armbruster, who's director of our school here at the University in Oceanography. And watch what happens. An event takes place. It could be a harmful algal bloom, it could be a volcanic eruption, it could be anything that changes the water. And you decide you want to study it by pumping the bacteria and the plankton through one of these little units. It's about the size of a trash can at home. It's a little factory, if you like. And you turn on the analytical button, and in seconds, you get genomic information about what's going on in the ocean. This is a breakthrough, and we're right on the threshold of that. And with the cable, we can do it remotely in 20 different locations, all related to one another, throughout the volume. Never been possible before. We're just at the threshold of being able to do this. Earthquakes. You know what happens during earthquakes? It turns out the seafloor breaks, of course. Water flows out, and it's full of microbes from below the seafloor. We think there are microbes that live well below the seafloor. We're pretty sure they are. And every time there's earthquakes, that rocks are broken, the fluid flows out carrying these microbes and chemicals and heat. But we don't know much about it. It's hard to get out there fast enough before the currents carry the output away. So a cable, something like this, on axial seamount, that's axial seamount there in the middle, could detect earthquakes. Let's say we're looking for earthquakes, and these are actual earthquakes that have taken place over the past 10 years. And we determined that up on axial seamount, the light color there, that the volcano is erupting. You can tell that because it has a sort of what's called harmonic tremor. And we send in the troops in the form of robotic vehicles. And they fly into, you know, you wouldn't do this if you were on your own Maserati, but you fly into the erupting plume and you take a sample. You launch it to the surface and you pluck it out of the water with something that might be called, what? A drone. How about that? We could use them. There's lots left. And snatch it out and bring it back to a place where it could be analyzed, like south end of Lake Union or the University of Washington. This is doable. We have all the pieces in place right now to do that. This is not crazy. This is very doable. All it takes is vision, commitment, persistence, and money. This is called Imagineering. The green balls are not touching each other. They communicate by optics, and they communicate all the way back to a pedestal which is connected to the fiber. The yellow balls are the sensor robots. They have 20 different sensors in them, and they can move around on their own. The orange balls are the navigation balls. They sort of occupy the corners, and they tell everybody where to go and what to do. And it's all connected back to land, and you are sitting there in your laboratory 10 years from now, and you're looking at this in a holographic projection. It's not on a flat screen. You're looking at it right out there, and you are controlling what's going on, and they are exploring a big black smoker chimney and the output in simultaneously from about 16 to 20 different points of view. They're all making measurements simultaneously as the whole thing evolves dynamically. How many of you remember 9/11? Probably everybody. Do you remember what happened on 9/7? Some people that lived in New York City, doctors, actually performed an operation on a woman in France, and they removed her gallbladder. 3,000 kilometers apart, yeah, through robotics. That was almost a decade and a half ago. If they can do that, I don't know why she agreed to it. That's a different story. But they successfully did it. We could do things on the seafloor that you wouldn't, that are unbelievable. We don't have to be there. With the right kinds of robotic systems, we can do things that nobody would imagine. This is not far-fetched either. It's just Imagineering. Now then, whales. You'll notice that the whales are a thread that runs through this whole presentation. We can have platforms offshore, or actually on axial seamount. We have reason to believe that whales are attracted to earthquakes and sometimes to hydrothermal systems and volcanic systems. We can test the hypothesis. But with the right kind of arrays, like we show the horizontal low-frequency line arrays there, we can actually reach out acoustically thousands of kilometers and track the vocalizations. We're not pinging the whales. We're not hitting them with any sound. We're simply listening. But with the number of these sensors, we can track their movement as much as 1,000 kilometers away, certainly hundreds of kilometers away, and track them and just sort of listen in, pay attention. That's possible here. And so what's really kind of cool from my point of view is when we talk about art and science is the science has allowed us now to record whales underwater at sea making sounds, and we can certainly do that now. But people like Paul Winter and Hovhannes and the fellow that you're about to hear, who is Michael Gettelson, or Gettel, with the San Juan suite, have taken the sounds of whales and melded them into music. So we have woven the technological advantage of being able to listen to whales underwater. We've woven that into our art as a community. I find this absolutely captivating, and I hope you will as well. You know that these creatures work together to corral food, and then one of them tells the other, okay, we've got these forms of food, and one will break off from the group. They're blowing bubbles to keep them corralled. One will go up through and fill their mouth and then come back. And they work together. It's really pretty fascinating. That's a side story. Here's the music by Michael Gettel. You know, it just occurred to me, sitting here watching this, if we went to another planet and we found an ocean, we found creatures like this in it, we would be absolutely captivated. Why aren't we captivated with this ocean? Why aren't we captivated with this planet? Why aren't we captivated with what we've got, which we are dependent upon? We need to pay more attention to the oceans. I'm going to move a little fast through this one, but I want to share this with you because this will be on your video screens in your own home when it happens. That's the center of the caldera right there. You see over on the right, you see the color. There's two white dots. Those are bottom pressure recorders. And here, and I have to explain this a little bit, here is measurements of the bottom pressure. On the left-hand side, it's converted to meters. So the seafloor in 1998 fell about 3.5 meters. The seafloor in the middle of the caldera dropped. At the same time, there was an eruption. And then the seafloor began to build up again. You see that slope, that sort of gentle slope there? The little dots began climbing up. And in 2011, the seafloor dropped about 2.5 meters here. And then we started watching it really closely, and instead of that sort of slow climb over there, this is what the pressure, the rise looks like. And here's 2012, 2014. The slope of the rise of the seafloor in the middle of that caldera is 4 times what it has been over the past 15 years. And that started about a year and a half ago. That volcano is going to blow. We don't know exactly when, but we guess it'll be within another year or two. We think it'll be after we get all our instruments in and all the cameras on and all the pressure sensors in place. And then, so I talked about this to some of the folks at NSF, and they said, what? You've got millions of dollars of our stuff out there, and you're putting it on a volcano? And I said, well, if you read all the reports that you funded, yeah. That one's going to come back, I think. I'll hear from that one again. But remember, this is excitement. This is how does the planet function underwater. This is really, really powerful. So what's that allow us? That allows us the opportunity to look at an entire ecosystem that is volcanic and overlying ocean, and we can map it out ahead of time, which we are doing right now, and we'll do more of it. This is axial in the middle, detailed system analysis. Here is an animation of what it might look like once we get it in place in another 10 years. We'll be making measurements of the entire overlying ocean in every way, and then we have the ability to react when Mother Nature decides to produce another underwater eruption, which no one has ever mapped out ahead of time, during, and after. Not just the sea floor, not just the eruption, not just the microbes coming out, which we've never seen before, but the entire effect on the overlying ocean. This is something nobody has done, and we're on the threshold of being able to do it because of that data I showed you earlier. And here's what we imagine. That is a little robot called Sentry, produced by Woods Hole folks. This is what we imagine it's going to look like. You see the edge of the caldera down there, and boom, it begins to erupt. Lava flows across the seafloor. You saw that earlier. A black cloud begins to build with microbes in it, with particles in it, with chemicals in it, with heat in it. And we'll be able to quantitatively measure exactly what's going on in this whole eruption, and then map out all the biology and all the chemistry and all the lava. This is really exciting. This is next generation science. And it's only one example. We could be doing things like this for all other kinds of systems in the ocean. I'm just showing you this because of my personal bias about volcanoes. But this is one of the many things we can be doing with this cabled system. So what's the long future? That's the next 5 to 10 years. What's the long future hold? Well, here's the perspective on a brilliant, brilliant man who wrote 2001, 2010, and 2065, I think. Arthur C. Clarke. He had 3 rules. Some people call them laws. They're just ideas. I love this one. This refers to people like me. When a distinguished but elderly, well, I'm elderly anyway, scientist states that something is possible, he's almost certainly right. When he states that something is not possible, he's almost surely wrong. Remember that. Well, if you're old, don't be a naysayer because nobody will believe you. The only way of discovering the limits to the possible is to venture a little way beyond them into the impossible. I actually subscribe to that philosophy. If you don't believe me, ask my wife, who's sitting here. This is the one I love the most. Any sufficiently advanced technology is indistinguishable from magic. Think about that. When you look at your cell phone, try explaining that to your grandmother 20 years ago. 20 years from now, these things will be embedded in your head. So the real voyage of discovery consists not so much in seeking new landscapes, but in having new eyes. Now, when Marcel Proust wrote this some years ago, he was thinking metaphorically. And, I think metaphorically as well, but it's actually true explicitly and technologically. And I'd like to explore some of what we're doing in the ocean. This is what's present in the ocean right now. We have a number of sites called ocean sites. It's an international program. And the red dots show where people are making measurements for a long time. We have Argo Floats. There's 3,600 of these all over the ocean, and they just float up and down. And when they get up, they signal to a satellite, and they go back down, about 1,000 meters. But they just go with the currents. It's a brilliant idea. It's been going for 3 decades, and it's producing lots of information on 3 or 4 different variables because that's all that can be put on them and which can communicate. And then there's submarine cables. Look at the distribution of submarine cables. What if every one of these could become an observatory, or all the new ones could become an observatory? Here's the way they got in place to begin with, about 1865 or 6. It was crude in those days, but it got data instead of 4 to 6 weeks going from North America to Europe. With this, they could communicate in seconds. Imagine what that could do to markets. Here's the way we do it now. This is what we did when we laid our cable. And here's where the cables are. Everything in blue is cable. We could turn the whole ocean into an opportunity to study the planet in new and different ways. We could do that within the lifetime of anybody here under 50. Why do I say that? Well, you've heard about Moore's Law. Moore's Law is the rapid increase in capability of computers. Very rapid. Look at this. If you were around in trying to store data back in 1983, 1 gigabit of data storage would have cost you about $183,000. If you did it today, the cost would be about 5 cents a gigabyte. Look at that. Everything is moving in that type of a direction. It's getting better and better, faster and faster, cheaper and cheaper, and smaller and smaller. And it's doing it exponentially. What does that tell you? That tells you several things. It tells academics like me that, we got to be very smart about how we educate young folks. We want to educate them to learn new things. It's an entrepreneurial world in every way you look at it. So we can't just teach them a few key things that they can use for the rest of their lives, and that'll bail them out. We need to teach people because they're emerging into a rapidly changing world. I love this guy, Kurzweil, Ray Kurzweil. Through booms and recessions, wars and peace, from Morse code to 4G, the trend curve, Kurzweil says, has continued uninterrupted. That's the plot I showed you earlier. If you understand the potential of these exponential technologies to transform everything from energy to education, you have a different perspective on how we can solve the grand challenges of humanity. That's important to think about, especially if you're in your 20s and 30s. So very quickly, every one of these technologies that I'm showing you here is changing exponentially and getting better and better, faster and faster, cheaper and cheaper, and smaller and smaller. Every one of them. And if you have the right platform, which is the cable observatory, you have the potential to put those into the ocean and dramatically transform the capacity that human beings have to be present throughout the ocean, not just in one place, not just in one ship, not just a satellite that sees the surface, but throughout the volume, entire volumes of the ocean. 20, 30 years from now, there'll be all sorts of cable observatories in the ocean. I will argue that delivering abundant power and unprecedented bandwidth into full ocean volumes can dramatically accelerate the rates of scientific and technological innovation. And we need that. We need that. Creativity is fostered by opportunity. For example, as I mentioned with this thing, this is where we'll bring you the ocean. We will bring it to your pocket. Everybody is going to be bringing it to your pocket. And this is a wonderful quote. I love this one too. Greg Suttel. We need to fundamentally change the way we think about talent, putting less emphasis on predetermined sets of skills and more emphasis on the ability to acquire new ones. We need to teach people to be innovative and be changing continuously for the better. These 3 kids, the 2 little girls on the left, are the 2 ladies in this. This is how long we've been working on this. These are the 2 ladies, and they're the same 2 people. But this is next generation science. This is next generation. This is the way people will do homework in the future. This is not far-fetched. This is just holography. And that's data. That's a whole planet scale of data on currents that they can look at any way they want. They can orient it any way they want. They can shift to temperature, they can shift to current, they can shift to all sorts of things. This is the next generation of education, and it needs data. So I'd like to end with this. T.S. Eliot won the Nobel Prize in 1948 for many things that he wrote, but the last major work was the Four Quartets, and he published those roughly 1943, depends on who you read, but they're beautiful poetry, and he has a rich and somewhat, arguably, some people say dense, I would say rich style. But one of the key elements of one of his poems, which speaks to me, is the following, which I think speaks for the whole human race, certainly speaks for most of the scientists I know and many of the young folks. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. Arrive through the unknown remembered gate, where the last of earth left to be discovered is that which was the beginning. At the source of the longest river, the voice of a hidden waterfall, black smoker. Not known because not looked for, but heard, half heard, in the stillness beneath the waves of the sea.